Hello, everybody. This is Sunday, it's September 12th, and I want to welcome you to the third week of our online astronomy course. I have a little bit of space news for you, and that is the launch date for the James Webb Space Telescope. That is a successor to the Hubble Space Telescope, is now the date for that is going to be December 18th. And so just a little bit after the semester ends, the James Webb Space Telescope is going to be launched. And that is, if that goes up and is successful, that is going to be the best Christmas present that astronomers could possibly get. But let's talk about Module 13 just a little bit. This is the module where we learn about how the universe works. And the most important force in the universe by far is gravity. Everything is moving around everything else because everything, moons orbit planets, planets orbit the sun orbits the center of our Milky Way galaxy. Our Milky Way galaxy is moving toward other objects in space, all because of the pull of gravity. And we have to learn, first of all, about how forces work. And to do that, we have to start with Isaac Newton. Isaac Newton was born here in this house that you see behind me. I took this picture when I was in Woolsthorpe, England, several years ago. And it's Isaac Newton. And he lived in this house all his life, but Isaac Newton revolutionized our understanding of the way things move with his 3 laws of motion. And his 3 laws of motion are really pretty easy to understand. And I'll just summarize them here for you. His laws of motion concern forces. And you know what a force is? A force is either a push or a pull, and that's all a force is, a push or a pull. And Newton's first law has to do with what happens if there are no forces acting on an object. And Newton's first law says that, and if there are no forces acting on an object, the total force is 0, then if an object is moving, it will keep on moving forever. If an object is at rest, it will stay at rest forever, unless an unbalanced force acts on it. So this is quite different than your intuition. Maybe you're thinking of pushing a grocery cart in the supermarket, and if you keep pushing that grocery cart, it keeps going. But if you stop pushing it, it comes to a stop. But Newton says you have to take a closer look at that, because as I'm pushing the grocery cart, what I'm doing is that I am balancing the force of friction that is opposing the motion of the grocery cart. You know, you can hear the squeaky wheels on your grocery cart. There's always that one wheel that goes blah, 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 blah. So if you keep pushing, then you are balancing the forces on that grocery cart. And so the net force on it, the total force on it is 0, and it keeps moving in a straight line at a constant speed. But as soon as I let it go, there's that unbalanced force of friction, and that's what slows the shopping cart down. So that's Newton's first law. And the important thing about the first law is that it says what forces do. As I said, it used to be thought that you need a force to keep something moving. And people still believe that today, that you have to keep pushing on something to keep it moving, because they don't realize that what they're doing is balancing the force of gravity acting against them. But that is simply wrong, according to Newton. Newton says what forces do is that they change motion. If a force acts on an object, then that object either speeds up or slows down or changes direction. 3 things that a force can do to an object to change its motion. It can speed it up, slow it down, or change its direction. Now, Newton's second law says how much an object's motion changes for a given applied force. And so force is related to an object's change in motion. And we call either a speeding up, a slowing down, or a change in direction, we call all three of those an acceleration. Right? In everyday language, acceleration means just speeding up. But in science, an acceleration is speeding up or slowing down or changing direction. And so how much of an acceleration do you get if you apply a force? That depends upon the object's mass, the amount of matter in an object. And in our course, we're going to measure masses in kilograms. So you can think of it this way. You know, if, let's just suppose I have a bowling ball, a big old bowling ball, and then I have a little tennis ball, both hanging by a thread connected to the ceiling, and they're just hanging there. Now, suppose I try to push the bowling ball. I try to push the bowling ball, and it swings out a bit, so its motion changes. It goes from being at rest to moving, swinging out. But if I push harder, it swings out faster. And so a greater force gives me a larger acceleration. On the other hand, if I push on that bowling ball, you get it to move, and then I push on the much less massive tennis ball, what's going to happen? The tennis ball with the same force is going to swing out a lot faster. It's going to have a greater acceleration. So the greater the force on an object, that tends to increase the acceleration. And the greater the mass, that tends to decrease the acceleration. And so that's the easy way of thinking about Newton's second law. Newton's third law is really amazing. Have you ever been in a crowded situation where maybe you're trying to get through a narrow gate, maybe at a ball game or a concert, and you're pushing the people in front of you and they're behind you pushing you? Well, Newton's third law describes that situation. It says that if I push on you, then you push on me back just as hard. The same strength force, but in opposite directions. In fact, if I push on anything, it pushes back on me just as hard, so it doesn't require a conscious effort to push. You can push on a wall, and if you push on that wall pushes your hand back just as hard. And you can feel that for yourself if you take a rubber band. So here's a rubber band. I'm going to hook that rubber band around my thumbs, so I can feel how this rubber band is creating a force between my two thumbs. One thumb is pulling on the other with this rubber band. And no matter how I stretch the rubber band, how I move my hands around, you can feel that those forces are always the same. I can amuse myself like this for hours. But that's the idea, that if I push on you, you push on me just as hard in the other direction. And we'll find out that in this module, that this explains why planets orbit the sun instead of the sun and everything orbiting Earth. So, a lot to learn about. And that's not all Newton did. Newton was a genius, the only person I can think of that rivals Einstein. And Newton lived here, and you can see over here, there's an apple tree. And the story has it, as Newton himself told a visitor, the visitor was sitting inside one of these little rooms, just he and Newton were looking out a window. And Newton recounted how one day he saw an apple fall from that tree. And Newton all of a sudden realized that just as gravity acts to pull objects to the ground here on Earth, that gravity also attracts the moon in its orbit around the Earth and keeps the moon moving around the Earth. And it keeps Earth orbiting the sun. And Newton came up with his law of gravity that describes how all of this works. And basically the idea is that everything that has mass, that has matter, attracts everything else that has matter. So if we were seated here and I was looking at you, you have mass, I have mass, and there would be a force of attraction between us. You would be attracting me and I would be attracting you because of our masses. If you have mountains outside, you're attracting those mountains and they're attracting you because of the mass. But what has the most mass of anything around us? And that is the solid Earth beneath our feet. And so basically the strongest gravitational force is the force that is pulling us down onto the surface of the Earth. So it's a wonderful tale about Newton's laws. And you'll also find out how Newton's laws allow us, Newton's law of gravity allows us to measure the mass of objects. If I have a large object and there's a small object going around it, and I can measure how large that orbit is, and I can measure the time for one orbit, the period of the orbit, then I can find out how big the mass is. And that's how we know how massive the sun is. That's how we know how massive stars are. It's how we know how massive Earth is. And so you'll find out about that too in this module. It's great stuff. This is one of the two really intense science parts of the course. Next week, you'll learn about light. But I hope you enjoyed learning about Newton. And I want to show you a little bit about what's in the sky tonight, or this week, I should say. So let me just share the screen here, and I'll pull up Stellarium. There it is. So this is on the evening of the 16th. And so this is, let's see, so you said 12, 13, 14, 15, 16, and that is Thursday night. You can see the moon is just going to be passing below Saturn. And so if you look at the south, this is around 10 at night, you'll see the moon right below Saturn. And it's really pretty. It's this Monday is first quarter moon. So let me zoom in here to show you the moon. So I'll just zoom in a little bit. And there is the moon. It's past first quarter by the time Thursday rolls around. And there it is right below Saturn. And then one night later, on the 17th, I'll advance this by a night. And the moon has moved over to be very close to Jupiter. So whether you go out on the 16th or the 17th, you should get a good view of the moon either below Saturn or below Jupiter. Well, I hope you enjoy learning about how astronomers understand all that they understand about how the universe works. Because as we go on, I'm going to be telling you some amazing things. And it's important to realize that they're all based largely on the ideas that Newton set out. So enjoy learning about this, and I look forward to seeing you next time. So until then, bye-bye.